electrons move from cathode to anode, setting up the flow of current from anode to cathode. This mode of operation is called as forward bias, and this current is called as a drift current. In the second case, we apply the battery in reverse direction. That is, we apply positive of the battery to cathode and negative of the battery to anode. As a result, holes are formed towards the negative of the battery and electrons from N side are pulled towards positive of the battery. Thus holes and electrons move away from the junction, which leads to an increase in the depletion region width. No current flows through the diode. This mode is called as reverse bias mode. But there are some minority charge carriers always present in both the regions. Hence, in the reverse bias case, minority charge carriers cross the depletion region, setting up the current flow. But magnitude of this current is very low, in nanoampere range. Ideally, in the reverse bias mode, current through the diode must be zero. But practically, we get some current which is called as the leakage current. Let's study the characteristics of this diode. This graph is drawn by considering external applied potential on x-axis, current flowing through the diode on y-axis. When the diode is operated in forward bias mode, current flowing through the diode between A and B remains at a low level. But as soon as the external voltage crosses the junction potential value, or cut in voltage, the flow of the current rises from point B and point C. This graph is called as the forward characteristics of a diode. When we connect the diode in reverse bias, the leakage current flows in the opposite direction till point D. But if we further increase the reverse voltage applied at one point, diode breaks down and a large amount of reverse current flows through it, which may damage the component. This value of reverse voltage is called as the breakdown voltage. In order to prevent our diode from breaking down, the diode should be doped in a very controlled manner. When an ordinary diode is heavily doped so that it has a very sharp breakdown voltage, it is called as the Zener diode. Thus, in the Zener diode, the breakdown voltage is accurately adjusted to make it withstand in the reverse biased mode. Hence, the Zener diode works effectively in reverse bias also. Due to this special characteristic, the Zener diode finds many applications in the voltage regulator circuits. The symbol and characteristics of the Zener diode are as shown. Thus, the only difference we get in these two types of diodes is that the PN junction diode doesn't work effectively in the reverse bias mode, increasing the probability of failure or breaking of component, whereas the Zener diode is specially used where controlled reverse bias operations are required, thus eliminating chances of component failure. There are many types of diodes available in the market which look identical but differ in their performance parameters. So how do we select the best type of diode suitable for use? We select them according to their specifications like DC resistance, AC resistance, diffusion capacitance, and transition capacitance, etc. Let's see what these parameters are. When the diode is operated in the DC voltage, the resistance of the diode is called as DC or static resistance. From the characteristics of the diode, this resistance is calculated by the ratio of V upon I. As DC source remains constant, we can compute V upon I ratio throughout the characteristics graph. During forward bias, current through the diode increases with the applied voltage. Hence, as the diode starts conducting, its resistance value goes down. Thus, during forward bias, the diode has minimum resistance. On the other hand, this resistance takes a very high value of mega ohms during reverse bias. DC or static resistance plays a vital role in the analysis of clipping circuits or rectifier circuits. When we operate the diode on the AC signal, its resistance does not remain same as that of DC or static resistance. This is because AC signals continuously change in a sinusoidal manner along the axis, taking alternate positive and negative values. Thus, this resistance becomes dynamic in nature. This dynamic resistance is calculated as dV upon di. This dynamic resistance comes in picture as an important parameter when we deal with the analysis of circuits that work on AC signals. During forward and reverse bias, the diode exhibits two types of capacitances: diffusion capacitance and transition capacitance. During forward bias, free electrons from N side cross over to P side, resulting in change in charge. This motion of electrons depends upon applied voltage. Therefore, diffusion capacitance is defined as the change in charge due to change in voltage during forward bias operation of the diode. CD equals dq upon dV. During reverse bias, we get change in a charge as majority charge carriers move away from the junction, leading to the capacitance called as transition capacitance, defined as change in charge due to change in voltage. CT equals dq upon dV. Let's have a quick review of what we've studied in this lecture. William Henry Eccles was the first who coined the term diode in 1919.